Welcome to G Fun Facts Online. Today we are diving deep into one of the most significant triumphs in the history of astrophysics, a story that spans over half a century and culminates in the groundbreaking discoveries of late 2025. We are talking about the definitive verification of Stephen Hawking's area theorem. For decades, this theorem was a ghost story of physics, mathematically beautiful but observationally impossible to prove. But thanks to the recent analysis of the golden event of January 2025, known as GW 250,114, we finally have the proof. To understand the magnitude of this discovery, we have to go back to 1971. A young Stephen Hawking was wrestling with the mathematics of general relativity, specifically looking at the event horizon of black holes. The event horizon is that famous point of no return. Hawking realized that unlike a physical surface, such as the skin of a balloon which can expand or contract, the event horizon is a mathematical boundary defined by light rays that are just failing to escape. He proved that under the strict laws of classical physics, the total surface area of a black hole's event horizon can never decrease. This became known as Hawking's area theorem. It sounds simple, but the implications are staggering. If you throw an asteroid into a black hole, the black hole gains mass and its horizon grows. If two black holes collide and merge, the area of the new, single black hole must be larger than the sum of the areas of the two original black holes. It can grow, or it can stay the same, but it can never shrink. This rule looked suspiciously like the second law of thermodynamics, which states that entropy, or disorder, in a closed system always increases. Jacob Bekenstein, a graduate student at the time, suggested this wasn't a coincidence. He proposed that the area of the black hole actually was a measure of its entropy. Hawking initially hated this idea because if a black hole has entropy, it must have a temperature, and if it has a temperature, it must radiate heat. That contradicted the very definition of a black hole, which was supposed to absorb everything and emit nothing. In an attempt to prove Bekenstein wrong, Hawking did the math and found that Bekenstein was actually right. This led to the discovery of Hawking radiation, the quantum effect that causes black holes to glow faintly and eventually evaporate. And here lies the great paradox that physicists have struggled with for 50 years. In the world of classical physics and general relativity, the area theorem says the horizon can never shrink. But in the world of quantum physics, Hawking radiation says the horizon must shrink as the black hole evaporates. Verifying the area theorem was about proving that in the violent, short-term chaos of a merger, where quantum effects are negligible, Einstein's classical rules still hold absolute power. For a long time, checking this was impossible. You cannot fly a tape measure out to a black hole. We needed to measure the size of a black hole before and after a merger. The window into this dark world finally opened with LIGO, the Laser Interferometer Gravitational Wave Observatory. On September 14, 2015, LIGO detected the first gravitational waves from a merger, an event called GW 150914. This signal was the first chirp heard around the world. It had three parts. First, the in-spiral, where the two holes spiral in and the frequency rises. Second, the merger, the chaotic moment they touch. And third, the ring-down, where the new, single black hole vibrates like a struck bell to settle into a stable shape. It took nearly 6 years for a team at MIT to analyze that split-second signal deep enough to test the theorem. In 2021, they managed to split the signal. They used the in-spiral to calculate the initial area of the parents, and the ring-down to calculate the final area of the child. They found that the area had increased from roughly 235,000 square kilometers to 367,000 square kilometers. The theorem held, but the confidence level was only 95%. In the rigorous world of physics, that is considered strong evidence, but not a discovery. The signal was just too short and too noisy to be certain. This brings us to the present day, late 2025, and the event that changed everything, GW 250114. On January 14, 2025, the upgraded global network of detectors, including LIGO in the US, Virgo in Europe, KAGRA in Japan, and the new LIGO India, caught a signal from a merger only 800 million light-years away. This was much closer than previous detections, resulting in a signal with incredible fidelity. Unlike the 2015 event, which was a short thud, GW 250,114 was described as a symphony. The detectors were sensitive enough to hear not just the fundamental frequency of the ring-down, but the overtones. Think of a bell. When you strike it, you hear a main deep hum, which is the fundamental mode, but you also hear higher-pitched shimmers called overtones. These overtones die out much faster, but they carry precise information about the shape and geometry of the bell. By analyzing these overtones in the gravitational waves, researchers could map the geometry of the final black hole with unprecedented precision. In September 2025, the results were published in Physical Review Letters. The confidence level was 5 sigma, or 99.999%. The horizon area increased exactly as predicted by Hawking's equations. This ruled out alternative theories of gravity that proposed exotic compact objects like gravastars or fuzzballs. We now know with near absolute certainty that when black holes collide, they obey the law. They are thermodynamic objects, they carry entropy. The ringdown we heard is the vibration of the event horizon itself, the sound of spacetime smoothing itself out. It proves general relativity is correct, all the way up to the edge of the abyss. However, there is a fascinating layer to this story regarding what physicists call echoes. The term has a double meaning. The classical echo is the ringdown we just discussed, which verified the area theorem. But there is also the search for the exotic echo. If Hawking radiation is real, and the thermodynamic connection is valid, then the event horizon might not be the clean, empty boundary Einstein predicted. Some theories, like string theory, suggest the horizon might be a physical surface or a quantum wall. If that is true, gravitational waves should just disappear into the hole. They should bounce off this quantum wall and come back out, creating a secondary echo that arrives milliseconds after the main ringdown. While the 2025 analysis confirmed the classical echo and the area theorem, researchers are currently scouring the noise floor of the GW 250,114 signal for these exotic echoes. Finding them would be the next revolution, potentially breaking the area theorem by showing where it fails due to quantum mechanics, finally uniting gravity and quantum physics. As we close out 2025, we stand in a new era of astronomy. We have confirmed that black holes are not just monsters of destruction. They are law-abiding citizens of the cosmos that store information and grow according to precise thermodynamic rules. The verification of Hawking's area theorem is a posthumous victory for Stephen Hawking, cementing the deep link between gravity, thermodynamics, and quantum information. The next generation of detectors, like the Einstein telescope and the Cosmic Explorer, are being designed to listen even deeper. They may eventually hear black holes effectively breathing, detecting the breakdown of the area theorem over billions of years as Hawking radiation takes over. But for now, the law holds, the area increases, and the legacy of Stephen Hawking is more vibrant than ever.